Hello and welcome to Engineers Mindset Academy. So in today's class, we are going to be looking at another most repeated topic in Jamb, which is the heat capacity. As you all know, at the end of all the discussion in each topic, we'll round up with 2 to 3 years past question review on every specific topic we deal with in our Jamb series. Alright, so sit tight while we begin the class. Welcome back. Now, let's talk about heat capacity. As we all know, heat can only be transferred between two bodies when there is a temperature difference between them. So one of the body must always be at higher temperature and the other body must always be at lower temperature. So whenever they come in contact, the one at higher temperature releases temperature to what the other one at lower temperature. So the process is what is called heat transfer. Now, heat transfer to a body is directly proportional to the mass of the body and to the temperature difference between these two bodies. So the heat transfer is usually directly proportional to the mass of the body and to the temperature difference between the two bodies. Mathematically, we can say that heat transferred is directly proportional to the mass of the body times the change in temperature between the body. And we all know that whenever we remove the proportionality sign, we always introduce a constant. So this simply means that the heat transfer to body is equal to mass times specific heat capacity times change in temperature, where C is a constant called specific heat capacity. C is simply a constant called specific heat capacity, and delta theta here stands for change in temperature. Okay, where delta theta stands for change in temperature and is simply given as delta theta 2 minus theta 1, which means the final temperature is theta 2 minus the initial temperature. Okay, theta 2 means the final temperature, theta 1 is initial temperature. So delta theta simply means change in temperature. And C stands for what? The specific heat capacity in this equation. Now let's find the value of the specific capacity from this equation. Now we have that H is equal to mc times change in theta. Therefore, let's make C subject. To make C subject, you have that C is equal to the heat supplied to the body all over mass times change in temperature. So this is simply what the formula to calculate specific heat capacity for a given what substance. Now, the specific heat capacity by definition, as can be seen here, is simply the quantity of heat which is required to raise the temperature of a unit mass of a substance by 1 degree Celsius or 1 degree Kelvin. It is simply the quantity of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius or 1 degree Kelvin. It is usually measured in joules per kilograms Kelvin. Okay, it is measured in joules per kilograms Kelvin. Now, falling back to this equation, heat is equal to mc times change in theta. The product mass times specific heat capacity gives us what is called the heat capacity itself or thermal capacity. The product of the mass and the specific heat capacity gives us what is called the thermal capacity or the heat capacity. Hence, heat capacity, okay, heat capacity, which is denoted as Cp, okay, is simply the product of mass times specific heat capacity. So if we look to this equation, we have that the heat supplied to a body is equal to mass times specific heat capacity times change in temperature. This simply means that heat supplied to a body equals, in place of mass times specific heat capacity, we call that thermal capacity Cp. Hence, we have what? Cp times change in temperature. So we can actually find what is now the thermal capacity or what is now the heat capacity, which is the subject of our topic of discussion today, heat capacity. Then, what then is heat capacity? If we make thermal capacity subject, Cp is simply equal to what? The quantity of heat supplied divided by change in temperature. All right, so this shows us that the thermal capacity or the heat capacity is simply the amount of heat required to raise the temperature of a body or an object by 1 degree Celsius or 1 degree Kelvin. Simply the amount of heat required to raise the temperature of a substance by 1 degree Celsius or 1 degree Kelvin. It is measured in joules per Kelvin. Okay, it is measured in joules per Kelvin, or you can simply say joules per degree Celsius. So this is the unit of this is the unit of heat capacity or thermal capacity. Now, the difference between the thermal capacity and the specific heat capacity is that specific heat capacity is the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius or 1 degree Kelvin, whereas the thermal capacity or the heat capacity is the amount of heat required to raise the temperature of a body by what 1 degree Celsius or 1 degree Kelvin. So what has been omitted amongst the two is what simply the mass. Hence, when we multiply the specific heat capacity by mass, we obtain the what thermal capacity or the heat capacity itself. All right. Now let's pick a slight example to actually explain these two concepts. All right. So let's consider this question on the board to explain the concept of heat capacity. It says, what is the quantity of heat required to raise the temperature of aluminium from 30 degrees to 70 degrees? Take specific heat capacity of aluminium to be 900 joules per kilogram per Kelvin. All right. So let's pick out our parameters. What is the quantity of heat required to raise 3 kg of aluminium? So the mass of aluminium mass was given to us as 3 kg from 30 degrees Celsius to 70 degrees Celsius. So initial temperature, okay, initial temperature, which is theta 1, was given as 30 degrees Celsius, and final temperature, which is theta 2, was given as 70 degrees Celsius. Now, we are given the specific heat capacity of aluminium to be 900 joules per kilogram per Kelvin. So, C aluminium is simply equal to what? 900 joules per kilograms Kelvin. Now, look through the question again. It says, what is the quantity of heat required to raise the temperature of 3 kg? And remember from definition, we said that the quantity of heat required to raise the temperature of a unit mass of a substance. So whenever mass is involved, you're simply talking about what? Specific heat capacity. Whenever mass is involved, we're simply talking about specific heat capacity. So the heat from specific heat capacity is given as what? MC times change in theta, because there is mass involved. And even in this question, we are given a mass of what? 3 kg. So you recall that heat supplied is simply equal to the mass of the aluminium times specific heat capacity of aluminium times change in temperature. Now, what is change in temperature? Okay, this is now equal to mass times specific heat capacity times the change in temperature. That simply means what? Theta 2 minus theta 1, which means the final temperature minus the initial temperature. Hence, the heat supplied or heat required is now equal to what? Mass of aluminium was given as 3 kg multiplied by specific heat capacity of aluminium was given as 900. Okay, now times the change in temperature. Final temperature was given to us as 70 degrees Celsius. So you have 70 minus initial temperature was given as 30. So this is 70 minus 30. So this is equal to 3, okay, times 900 times 70 minus 30 gives us 40 degrees Celsius. So let's simply obtain those multiple. This will imply that the heat supplied is equal to, that gives us 108,000 joules. Okay, so this is the quality or the quantity of heat required to what? Raise the temperature of 3 kg of aluminium from 30 degrees to 70 degrees. Simply 108,000 joules. Let's pick another question and also to further explain the difference between the thermal capacity or the heat capacity and the specific heat capacity itself. All right, so let's consider the second question on the board. Question says, a copper rod of heat capacity 585 joules per Kelvin is heated until its temperature changes from 35 degrees Celsius to 85 degrees Celsius. Question says, calculate the quantity of heat supplied. If the specific heat capacity of copper is 390 joules per kilogram per Kelvin, find the mass of copper. All right, so this is actually two questions in one. Let's pick out our parameter. The first question says a copper rod of heat capacity 585 joules per Kelvin. So heat capacity, which is Cp, is given as 585 joules per Kelvin. So be very careful. Cp is heat capacity or thermal capacity. Okay, a copper rod of heat capacity 585 joules per Kelvin is heated until its temperature changes from 35. So initial temperature, okay, which is theta 1 is equal to 35 degrees Celsius, and final temperature, which is theta 2, is equal to, until it changes from 35 to 85 degrees Celsius. So final temperature is 85 degrees Celsius. The question is asking us to calculate the quantity of heat supplied. Now, this brings us to the idea of what? Heat capacity or thermal capacity. And I said heat capacity is simply the product of the mass of a given body towards the specific heat capacity. But in this question, we are not going to consider, we are solving the first part of the question. There was no specific heat capacity given to us. So we are going to solve as if there is no specific heat capacity in the first part of the question. We are asked to find thermal capacity, and I simply said that thermal capacity can be given as what? Heat divided by change in temperature. So the heat required to raise the temperature of a body by 1 degree Celsius or 1 degree Kelvin gives us the thermal capacity. Hence, Cp is equal to heat all over the change in temperature. This is simply what? Heat all over theta 2 minus theta 1. Now, we are asked to find the heat required or heat supplied. So we were given the thermal capacity Cp. Hence, we make heat subject of the formula. If we make heat subject, the heat required becomes what? The thermal capacity multiplied by change in temperature. So the heat required simply is the heat capacity of an object multiplied by the difference in temperature. So I always say that whenever mass is not involved, we are simply talking about what? Heat capacity or thermal capacity. But if mass is involved, then you talk about specific heat capacity. Now we are given the thermal capacity Cp. We know the temperature differences. We can impute them. Then we can now solve. Now this is equal to, the thermal capacity was given as 585 multiplied by temperature difference is simply what? From 85, okay, to 35. So you have 85 minus 35. Hence, the heat required is equal to, we have 585 multiply 85 minus 35 obviously gives us 50 degrees Celsius. Hence, the heat required or heat supplied is equal to 585 multiplied by 50. That simply gives us 29250 joules. Hence, the heat supplied is simply 29250 joules. Now, the second part of the question says, find the mass of copper if the specific heat capacity of copper is given as 390 joules per kilogram Kelvin. So now we are given specific heat capacity, okay, specific heat capacity, and we know that to simply be what? C is 390 joules per kilograms per Kelvin. So if this is specific heat capacity, we are now asked to find the mass. So you recall that I said earlier that the heat capacity is simply what? The product of mass and specific heat capacity. It is simply the product of mass and specific heat capacity. So if we know the heat capacity and we know the mass, we can simply use what? This relationship to find what? The mass. Hence, you recall, okay, that Cp, which is specific, which is heat capacity, is equal to what? Mass times specific heat capacity. Now we know the specific heat capacity, we know the heat capacity, we can make mass subject. Therefore, mass is equal to what? The heat capacity divided by specific heat capacity. This implies that the mass of the body is equal to, heat capacity was given to us as 585 divided by the specific heat capacity itself is 390. This simply implies that the mass of copper will now be equal to 585 divided 390. That gives us 1.5 kilograms. Hence, the mass of the object is 1.5 kilograms. So it's always important for you to know these relationships by their definition. Okay, it's very easy from the definition. You can easily pick it out or know it. The heat capacity is simply mass times specific heat capacity, and then conversely, you can as well find the value of the specific heat capacity. But whenever it relates to mass, we are simply talking about what? Specific heat capacity. When there is no mass involved, we're simply talking about what? The heat capacity itself. All right, so having talked about heat capacity, let's talk about a different concept which is called latent heat. From our day-to-day activity, we know that if you bring ice at its melting point, which is 0 degrees, and you add temperature or you add heat to it, after some time, the ice absorbs this heat and completely changes into water, but the temperature still remains what? 0 degrees. This property in ice which absorbs this heat is unseen. It absorbs the heat and completely changes this ice from solid to liquid, which is water, is called latent heat. So latent heat is simply the heat which is inherent in a body, which causes a change of state of a body without a change in temperature of the body. It is simply a heat inherent in a body which can cause the change of state of a body without changing the temperature of the body. It is simply called latent heat. Now, there are different forms of latent heat. We have the latent heat of fusion, latent heat of fusion. Okay, we have the latent heat of fusion. Okay, latent heat of fusion. So since we know that fusion is simply the process whereby an object or a substance changes from its solid state to its liquid state, and we know that latent heat is simply that property of a body which can cause an object to change from one state to another without a change in temperature. Hence, we can define latent heat of fusion as simply that heat which causes a unit mass of a substance to change from its solid state to a liquid state without a change in temperature. The heat which causes a substance, a unit mass of a substance, to change from its solid state to a liquid state. Mathematically, latent heat of fusion, always represented as small l, okay, is simply equal to the heat required to change a unit mass of a substance from its solid state to its liquid state without a change of temperature. All right, so if we make the quantity of heat subject here, we are going to have that this implies that heat supplied to an object under latent heat is simply equal to what? Mass times the specific latent heat of fusion. Okay, where L is simply called the specific latent heat of fusion. Where L is simply called the specific latent heat of fusion. It's right. So from here, the unit of the specific latent heat of fusion is simply given as what? Joules per kilograms, because as can be seen here, unit of heat is joules and unit of mass is kilograms. So the unit of the specific latent heat of fusion is given as joules per kilogram. So simply, if an object converts or changes from solid state to liquid state without a change in temperature, then we said the property that causes this change is called latent heat of fusion. And mathematically, it can be given as what that. L stands for the specific latent heat of fusion and simply given as heat all over the mass of the body. So it means that the heat supplied to an object undergoing fusion is simply given as what? The product of the mass of the body by the specific latent heat of fusion. All right, so let's pick another example to explain this before we can talk about the final term, which is specific latent heat of vaporization. All right. All right, so let's consider this question. It says, how much energy is required to change 5 kg of ice at 0 degrees Celsius to water at the same temperature? Take the specific latent heat of fusion of ice to be equal to 360,000 joules per kilograms. Okay, so let's pick out our parameters. we were told how much energy is required to change 5 kg. So we are given mass M to be equal to 5 kg of ice at 0 degrees to water at the same temperature. Take the specific latent heat of fusion, and we're given L, which is specific latent heat of fusion, to be equal to 360,000 joules per kilograms. Okay, we are asked to find the what? Energy. Energy simply means the heat required or known. So if you're asked to find energy, energy simply means the heat required or the heat supplied. So I've said earlier that the heat which is caused or required to change a substance from a solid state to a liquid state without a change in temperature is simply called the heat of fusion. As can be seen here, this question highlighted that how much energy is required to change 5 kg of ice at 0 degrees to water at the same temperature. So the temperature still remains what? 0 degrees, it didn't change. Automatically that becomes what? Latent heat of fusion. And you recall that from the formula, the heat supplied under fusion is given as what? The mass times specific what? Latent heat of fusion. So this is equal to mass was given as 5 kg multiplied by what? The latent heat of fusion was given to us simply as 360,000 joules per kilogram. All right, so from here, you can simply have that the heat required becomes what? 5 times 360,000. Let's obtain that value. So that gives us about 1.8 million, which is 1.8 by 10 to the power of 6 joules. So this is the number of heat required. 1.8 million joules of heat is actually required to convert ice at 0 degrees Celsius to water. Okay, so that becomes the answer to that particular problem. Now, just like we've defined fusion, we can also have latent heat of vaporization. And we all know that vaporization is simply the process whereby a substance changes from its liquid state to a gaseous state, or from its liquid state to a vapor state. Hence, latent heat of vaporization is that quantity of heat required to change a unit mass of a substance from its liquid state to its vapor state without a change in temperature. So when there's no change in temperature, we are simply talking about what? Latent heat. So mathematically, latent heat of vaporization, also represented as what? L, is simply what? The heat required to change a unit mass of a substance. So it has the same formula as what? Latent heat of fusion, with the only difference is that this is now latent heat of vaporization, where L in fusion stands for latent heat of fusion. Hence, from here, you can find that the heat supplied under vaporization stage becomes what? Mass times the latent heat of vaporization. Okay, so the unit for L here also remains joules per kilograms, and unit of heat always remains joules. So that is the latent heat of vaporization. All right, guys, so I'll pause the video here and we can now start our past question reviews. Let's check out past questions on this particular topic that have occurred over time in the Jamb examination. So sit tight, watch through the end to get everything in details. Thanks. Welcome back. All right, so let's consider the first Jamb question we are reviewing. This is Jamb 2021 question. This is exactly question 32. It says, calculate the mass of ice that will melt when 2 kg of copper is quickly transferred from boiling water to block of ice without heat loss. Take specific heat capacity of water to be 4,200 joules per kilogram Kelvin and the latent heat of fusion of ice to be 3.3 by 10 to the power of 5 joules per kilograms. All right, let's pick out our parameters. We are asked to calculate the mass of ice that will melt when 2 kg of copper. So we are given mass of copper to be 2 kilograms. Mass of copper equals 2 kilograms. Okay, is quickly transferred from boiling water to block of ice without loss of temperature. Okay, without loss of heat. Now we are given specific heat capacity of water. C of water was given to us as 4,200 joules per kilograms per Kelvin, and we're given the specific latent heat of fusion of ice, L of ice, to be equal to 3.3 by 10 to the power of 5 joules per kilogram. So we have to find the mass of ice. Okay, now let's start with the latent heat of fusion. We know since ice changes from solid to water, then we know that latent heat is given as H, and that's equal to mass times what? The latent heat of fusion itself. Now, this is the formula for latent heat of fusion. Okay, this is formula to calculate latent heat of fusion. Heat equals mass times L. Now, since ice is changing, it means this is the mass of ice which we are asked to find, and this is the or the specific latent heat of fusion L. Okay, so this is equal to, now we don't know the mass, so you put it down, m times the specific latent heat of fusion was given to us as this, which is 3.3 by 10 to the power of what? 5. So which means that the heat of fusion H is equal to 3.3 by 10 to the power of 5 times mass, keeping this aside. Alright, so this is the heat required to melt ice from solid state towards liquid state. So let's now calculate what is the heat required to boil 2 kg of copper from 0 degrees Celsius to 100 degrees Celsius. Of course, it says copper was transferred quickly from boiling water. Okay, so it was transferred from 0 degrees Celsius to boiling water because the temperature of boiling is simply what? 100 degrees Celsius. Okay, that is simply obtained by using the equation heat capacity is equal to mc theta for specific heat capacity, where theta means the change in temperature. Now, this is the heat required to boil copper. Therefore, this is equal to the mass of copper was given to us as 2 kg. You put it down 2 times the specific heat capacity of water was put there as what? 4,200. So you have 4,200 joules per kilogram per Kelvin times the change in temperature. Now, what is the change in temperature? At the ambient temperature, copper has 0 degrees Celsius. Now, after boiling, copper has 100 degrees Celsius. Of course, for a water to boil, it must be up to 100 degrees Celsius. So we have 100 minus 0 degree Celsius. Therefore, the heat required to boil copper becomes what? 2 times 4,200 times 100 minus 0 still remains what? 100. And the whole of this will give us 820,000 joules. Okay, so this is the total heat required to boil copper or transfer copper quickly into a boiling water. Now, having obtained this, the heat of fusion and this heat must be what? The same. The heat of fusion and this heat must be the same. So we simply equate the both of them together. Therefore, we are going to have that this heat, which is 820,000, is now equal to the heat of fusion, which is given as 3.3 by 10 to the power of 5 times mass. So from here, we can find mass or make mass solve the formula. Therefore, mass becomes what? 820,000 divided by 3.3 by 10 to the power of 5. So let's obtain the value of mass.